Hello everyone, I hope you are doing well. My name is David Dias and I am here to talk a little bit about my master thesis project and my expectations from it. I am working at LEAP on the improvement of neutrino detection at the Pierre Auger Observatory.
First of all, neutrinos are almost massless particles with no charge, which very rarely interact. For these reasons, when emitted from an astrophysical source, they easily escape it and travel in a straight line without deflection or absorption, so they can be used to determine the source's direction. This is particularly relevant in the context of multi-messenger astronomy, which is a technique which combines different messengers from one event to obtain more information about it. The most common of these messengers are charged particles, such as protons or ions, which are known as cosmic rays. Their spectrum is composed of a few features, but overall, the flux decreases with energy up until a cutoff predicted by the GZK effect. The most extreme sources can produce cosmic rays in the ultra-high energy region, which, for the case of protons, can lead to the creation of ultra-high energy neutrinos, but so far none have been detected. When reaching the Earth, these highly energetic particles interact with the atmosphere and form a shower, or cascade, which typically has three components. The hadronic component is closely tied to the muonic one, so you can use the muonic signal, S-mu, to infer information on the hadronic cascade, which, due to the extremely high multiplicities per interaction at these energies, will most likely not reach the ground. At the same time, an electromagnetic cascade competes with its hadronic variant, and its signal upon reaching the ground observation level is known as SAM. These cascades typically present Gaussian-like longitudinal profiles, and the depth at which the maximum number of particles is present is called Xmax. Pierre Auger Observatory in Argentina was built to detect ultra-high-energy cosmic rays, but has conducted searches for ultra-high-energy neutrinos using techniques like Earth-skimming neutrino detection, where the event direction can only be compatible with a particle which interacts as little as a neutrino does. This technique is very effective, but severely limits the observatory's acceptance because it only covers a very small band of the sky. Recently, Pierre Auger's detectors were upgraded with scintillators and radio antennas, enabling detailed measurement of shower development features. This upgrade opens new possibilities for directly measuring and distinguishing SAM and S-mu. To solve the coverage problem, these signals can be used during the analysis of vertical events to distinguish between neutrino and proton-induced showers, since their depth of first interaction can be very different due to the low interaction probability of the neutrinos. To separate the two simulated populations, a Fisher linear discriminant analysis can be performed to extract the array's neutrino detection efficiency for any given background rejection factor. Since no neutrinos have been found, we can then use this efficiency to impose upper limits on the differential neutrino flux. The results I've obtained so far, despite not being amazing, seem to indicate that this is worth researching, since vertical neutrino event detection would boost our sky coverage to its maximum. To improve this detection efficiency, my master's thesis will focus on using Xmax information to further increase the distinction between proton and neutrino events. To accomplish this, I first started by fitting my simulated events to a Geiser-Hilles function. Afterwards, I split my events in Xmax bins and performed the same Fisher-cut analysis as before. In some Xmax bins, the distinction between signal and background visibly increases. However, the Fisher-cut encountered some inconsistencies due to the low statistics per bin. To resolve this issue, I will switch my approach to a boosted decision tree analysis. I will also explore the possibility of extracting the longitudinal profile from the radio antennas installed during the upgrade.
Thank you for your attention.